Now that we have data sets imported into our SSP project, we can create and compute analyses. SSP currently has 11 analysis types shown here. I'll briefly describe each in this lecture and demo 2 of them. The Bulletin 17 analysis is the most frequently used analysis type in SSP. The Bulletin 17 analysis implements a strict flow frequency analysis in accordance with Bulletin 17B or 17C procedures. Bulletin 17C refers to current federal flood frequency guidance in the United States. The Bulletin 17 analysis also allows users to evaluate a moving or expanding time window, which I'll demonstrate later. A dataset must be irregular in order to be used in a Bulletin 17 analysis and must contain one and only one peak in each water year. We have an entire lecture and workshop dedicated to Bulletin 17 analyses later in this class, and we talk about this topic extensively in our flood frequency analysis class. The general frequency analysis allows users to implement a frequency analysis on flow, stage, precipitation, or other data that is less strict than the Bulletin 17 procedures. This analysis provides users with numerous analytical distribution and fitting method combinations. Users can manually define distribution parameters and compute a graphical or empirical distribution. Annual maximum series or partial duration series is selectable within this analysis. The general frequency analysis requires the use of irregular data, specifically IR century data. The volume frequency analysis allows users to compute an iterative or duplicative frequency analysis. Frequency curves are developed using flow time series that are averaged over user-specified durations. Runoff volumes are expressed as average flows over a time duration. For example, the 3-day flow is the average flow over a 3-day period. The analysis then extracts an annual maximum series from each of these n-day averages and fits a distribution. Numerous analytical distributions and distribution fitting method combinations are provided. Users can manually define distribution parameters to smooth statistics, and graphical or empirical distributions can be used. The volume frequency analysis requires regular data, and specifically 1-day data or mean daily flow is typically used. The duration analysis computes stage or flow duration curves, which specify the percent of time that a given stage or flow value was exceeded. There are 2 methods to do this, the rank or sort, or the stats method. The rank method sorts all values, while the stats method groups values into bins. The user can also specify annual, quarterly, monthly, or user-defined periods to use all or a subset of the data. The duration analysis requires regular data. The curve combination analysis graphically defines an empirical distribution for 2 or more input frequency curves. The input frequency curves can be specified as the results from other analyses, such as a Bulletin 17 or general frequency analysis. The coincident frequency analysis uses the total probability theorem to compute a frequency curve that is a function of 2 variables, A and B. The user can select from one of 2 conditions, that variable A and B are independent, or that variables A and B are not independent. Variable A is a flow or stage frequency curve, and variable B is index points from a flow or stage duration curve. The analysis computes a series of response curves for the user. We have an entire lecture and workshop dedicated to coincident frequency in this class. The mixed population analysis uses the total probability theorem to compute a frequency curve from 2 or more different runoff or flood causal mechanisms. Flood causal mechanisms can be rainfall, rain on snow, snowmelt, tropical storms, or other mechanisms that cause floods. When annual peak flows at a site are caused by multiple mechanisms, the flood series cannot be considered identically distributed, and a mixed population analysis should be performed. The resultant empirical distribution takes into account the relative probability of a flood occurring in any year due to any of the input runoff mechanisms. The input curves in the mixed population analysis can be results from other analyses, such as the Bulletin 17 or general frequency analyses. The next analysis type is the balanced hydrograph analysis. Balanced hydrographs are hydrograph shapes that are based on observed or synthetic flood hydrographs and have been modified to contain specific exceedance flow rate or volumes across one or more durations, as shown in the frequency curve on the right of this screen. This can lead to unrealistic hydrograph shapes, such as a stair-step hydrograph, so you want to be careful when performing this analysis. Sometimes the longer duration has a rarer exceedance, while other times the shorter duration has a rarer exceedance. These situations are indicative of different flood-generating mechanisms. For example, snowmelt-driven floods will show longer durations having a more rare exceedance, since peak flows might be relatively small in magnitude. On the other hand, convective storms will produce shorter durations that have rare exceedance probabilities, since the flood event has a relatively small volume but large peak. Results from other analyses, such as the Bulletin 17, general frequency, or volume frequency analyses, can be imported into the balanced hydrograph analysis. In addition, regular data is required. The correlation analysis was introduced in SSP version 2.3 and is used to compute the amount of linear correlation between various data sets, such as tributary peak flow versus main stem stage, as shown on the right, or 3-day precipitation volume and 3-day average temperature, or annual maximum SWE and annual maximum 24-hour precipitation accumulation. The analysis provides 3 computation methods: time series coincident events, time series coincident in time, and paired data. When selecting coincident events, the user specifies an event length, n. Events are then considered coincident if they occur within n days of each other. This can be used to help inform selection of sites for an annual peak flow record extension using Move3 techniques, which I'll talk about next. Coincident in time means that values from the secondary time series are extracted at the same time as each of the values within the primary time series. This can be used to help inform a coincident frequency analysis. The paired data method is used to determine how closely related the values within a paired data curves are. These curves are specified with no date or time axis. In the correlation analysis, results from a Bulletin 17 analysis can be imported, and both irregular and regular data is accepted. The record extension analysis was also introduced in SSP version 2.3 and can be used to extend a short record site, such as the one shown in blue on the right, using a longer record site, such as the one shown in green. The analysis provides users with multiple computation methods. Move stands for Maintenance of Variance for Extension. Move3 is documented in the Bulletin 17C document and should be used to extend a record that will then be used for peak flow frequency analyses, such as Bulletin 17 procedures or volume frequency analyses. The Move1 method is used to create an extended regular time series that can then be used in applications such as a duration curve or low flow analysis. This analysis is incredibly impactful in adding to the information content of a data set. Both irregular and regular data types are accepted in this analysis. The last analysis type that I want to talk about is coming soon in version 2.4, and that's the peaks over threshold analysis. This analysis allows users to compute an annualized frequency curve and confidence limits from a partial duration series. This is useful when a system experiences multiple floods or extreme events in a year and none in other years. This analysis is also powerful because it allows users to visualize diagnostic data, such as the plots shown on the right, to help inform selection of an appropriate threshold. Users can use both irregular and regular data in this analysis. We'll talk more about this topic in the Extreme Value Theory lecture and workshop, as well as the Peaks Over Threshold workshop.